Now that we've talked about linear equations, we're going to talk about linear inequalities in one variable. We assume that the viewer has some familiarity with intervals and interval notation, but really quickly we'll give you a quick refresher slide. So intervals from a to b are just going to be the sets that contain all numbers from a to b, and we're going to use either square brackets or open brackets to indicate whether or not those endpoints are actually included. So below are the set of bounded intervals and a picture of the number line that they represent. We can also talk about intervals that go off to positive or negative infinity. It may have a left endpoint or a right endpoint, or be open at both ends by going from infinity to infinity, which would just denote the entire real line. We also know that real-valued endpoints like a can either be included or not included, but the infinities will always get an open bracket. Suppose we're talking about a portion of the number line that's been cut in half. So maybe I have the interval from -3 - 1 and from 0 to 4. If I want to combine these together, I use what's known as the union. It looks like this U symbol where I write these disjoint intervals next to each other. So this is how we denote the collection or the union of these disjoint line segments. Another example would be the following. If I've got the interval from -infinity to -2, then 0 to 3, then 5 to 9, then I can write that in the following way. Again, this portion of the video was pretty brief, but we are assuming that a Mat 130 student does have some familiarity with intervals. But if you do need a bigger refresher on this, please reach out to your instructor. So first and foremost, an inequality is a relation of a mathematical expression which involves one of the symbols less than or equal to, greater than, or greater than or equal to. To be specific, the symbols less than or greater than, we call those strict inequalities, while less than equal to or greater than equal to are weak inequalities. The nice thing about this section is a lot of our strategies for solving linear equations carry over into linear inequalities. We pretty much just have two main differences. The first is that of our solution set. A linear equation can have one or maybe even two solutions when we are dealing with absolute value equations, for instance. However, with linear inequalities, we will most likely have infinitely many solutions because we're going to express our solution set as an interval. For instance, we're going to have answers like x less than 4 as opposed to x equal to 4, and there are infinitely many numbers less than 4. So that's why we have infinitely many solutions to these types of inequalities. Next, we're going to talk about a new rule that says that an inequality changes direction whenever I multiply or divide both sides by something that's negative. So why is this the case? Suppose I have the statement -3 less than 2, which is certainly a true statement. What happens when I multiply both sides by 1 and don't flip the inequality? I get the statement 3 is less than -2, which is clearly false. So the correct statement to write is that 3 is now greater than -2. At the end of the day, multiplying or dividing both sides by something negative of an inequality is still a legal math move, but when you're doing this, you're basically flipping the number line, so that's why we change the direction of an inequality. Note that this rule only applies when I'm multiplying or dividing by something negative. If I multiply or divide by something positive, then the inequality does not change direction. Next, suppose you had the inequality -3x plus 2 is less than or equal to x. If I multiply both sides by -1, I'll end up with positive 3x minus 2 is now greater than or equal to -x. So the only thing that ever changes about an inequality when it flips is the fact that it's flipped. Strict inequalities don't change to weak inequalities, and weak inequalities don't become strict inequalities. For our first example, we're going to solve the following inequality for x. 7 minus 3 times x minus 3 is less than or equal to -1 minus x. As I've said before, we get to carry over a lot of techniques from the previous sections about linear equations. I'm going to start simply by simplifying the left and right hand sides. To isolate the variable x, I'm going to subtract an x from both sides and subtract a 16 from both sides. This is going to land me at the inequality -4x is less than or equal to -17. The next natural step is to divide both sides by -4, but that's going to flip my inequality. So I'm going to get that x is now greater than or equal to 17 divided by 4. We're going to need to express our solution set in terms of an interval, and usually it helps to draw this on the number line to do so. I have a weak inequality, so I'll put a closed circle over 17 over 4 on the number line. And since x is greater than or equal to 17 over 4, I'm going to draw the arrow in the right direction. This is going to give us the solution set of the interval 17 over 4 to infinity, where 17 over 4 is included. In our next example, we're going to solve for a. Consider the inequality 3 times a plus 2 over 2 less than 5a over 4. One of our last videos showed us multiplying both sides by the LCM, or the least common multiple of the denominators. In our case, that's going to be a 4. So if I multiply both sides by a 4, it's going to clear out all of our fractions. And since I'm multiplying by a positive 4, it doesn't change any inequality directions. Next, let me simplify the left and right hand sides as much as I can. I'm going to get 6a plus 12 is less than 5a. Next, I'm going to subtract a 6a from both sides to give me 12 is less than negative a. And now to solve for a completely, I'll divide both sides by negative 1 and get that negative 12 is bigger than a. Next, I'm going to mirror this inequality so that a is on the left-hand side and write it as a is less than negative 12. Note that I have not actually flipped an inequality. I've mirrored the entire expression. Notice that on both the second to last and the last line, a is still the lesser of two quantities. It's just more conventional and easier to read and to draw on a number line when you have your variable on the left-hand side. To sketch this on a number line, I'm going to put an open circle above negative 12 because I have a weak inequality, and since a is less than negative 12, I'm going to point the arrow to the left. Therefore, I have a solution set of negative infinity to minus 12, where 12 is not included. In our next video, we're going to talk about compound inequalities. We use the word compound because we essentially have two inequalities working together simultaneously. For example, let's find all solutions for x so that negative 2 is less than negative 3x plus 4 is less than 16. The way to understand this is the following. The expression negative 3x plus 4 is trapped in between negative 2 and 16. So we need to find all values of x for which negative 3x plus 4 is between minus 2 and positive 16. Ultimately, that's all what's happening here. Another way to view it is this. I have that negative 2 is less than negative 3x plus 4, and that negative 3x plus 4 is less than 16. So again, it's like I have two things happening at the same time, which is why I call it a compound inequality. So let's write our original problem in the middle of the board and solve for x. Solving for x in this context means isolating x in the middle. But to make solving this a little bit more clear, imagine it this way. Cover the less than or equal to 16 with your hand, and then you just have the inequality negative 2 is less than negative 3x plus 4. What would be the natural step? It would be to subtract 4 from both sides. Do the same thing, but cover negative 2 less than with your hand, and now you just have the inequality negative 3x plus 4 is less than 16. Again, the step is the same, subtract 4 from both sides. So the way that we're going to say it here, to solve for x in the middle, is to subtract 4 from all sides of the inequality. So we can write that out in the following way. Subtract 4 from everything, and then we get negative 6 is less than negative 3x is less than or equal to 12. To isolate x in the middle, what we're going to do next is to divide all sides of the inequality by negative 3. Again, if it was just one inequality at a time, then division by negative 3 would be the natural step. So let's divide everything by negative 3, but then flip all the inequalities when we're done. This is going to give us the final result of positive 2 is strictly less than x is less than or equal to negative 4. Now, to make our solution a little bit more readable, I'm going to mirror this inequality so that my smallest numbers are on the left and my largest numbers are on the right. This is going to give me negative 4 less than or equal to x strictly less than 2. I draw it this way because now I can visualize it a little bit more easily on the number line. I know that x lives between negative 4 and positive 2, so my solution set will be the interval from minus 4 to positive 2, with negative 4 included and 2 not included. So this is the strategy for this type of compound inequality. The goal is to isolate x in the middle using the same kind of moves that we're already used to using. We subtract things from all sides, divide things by all sides, and flip inequalities as needed. And then we see that our solution set has x trapped between two numbers on the number line. Another style of a compound inequality might look like this. I'm going to solve 3x plus 4 less than 2x plus 3, or 7x plus 3 is greater than 6x plus 5. Now, this or doesn't mean solve one or the other. We still have to solve both. It just means that the final answer will be the union of the first inequality solution and the second inequality solution. So let's solve that first one. We can subtract a 2x and a 4 from both sides and land at the solution x is less than -1. For the second inequality, we'll subtract a 6x and subtract a 3 from both sides and end up with the solution of x is greater than 5. Now we have to combine our intervals, so let's draw both of these line segments on the number line. Then, when we look at the interval that represents these two line segments together, it'll be the union of -∞ to -1 and 5 to infinity.